This is Lecture 1 for Chapter 5, Atmospheric Circulation and Wind Systems. And we are going to start off this lecture right off the bat with a question. Why does understanding the wind matter? Well, wind affects our climate, our daily weather, our daily activities. Understanding the wind allows us to predict storms, which helps keep us safe. Understanding the wind is crucial for sailing and for navigation and aviation, any of our traveling activities. If we need to know about the wind to know where and when to plant crops, where or where not to build structures, and what types of structures to build. Wind, it's even important for energy production. Wind affects wind turbines and the energy that they produce. So understanding the wind is important for sustainable energy. So basically, understanding the wind matters because by understanding it, we can help keep ourselves safe, comfortable, and support our various industries. So getting right into it, how do we measure and map the wind? Well, if you're talking about measuring the wind, you are probably interested in wind speed and wind direction. We have a couple of different instruments and tools that we use to measure both of those things. Off to your right here, I believe this is some kind of NOAA sensor buoy out in the middle of the ocean floating around, and it's equipped with all of these different weather sensors. A lot of it measures wind. As you can imagine, being out on the ocean, understanding wind and what's going on be pretty important. So to measure wind speed, we use an instrument called an anemometer. To measure the wind direction, we can use something called a wind vane or a weather vane. And if you've ever seen like a little metal rooster or horse or something spinning on a little spindle up at the top of somebody's house, that is a weather vane. It's just a little paddle that's mounted on a vertical rod that spins, and you can see which way that paddle is moving, where it's pointing to see how the wind is coming direction-wise. We also have something called an arrow vane, which is kind of multi-purpose. You can both judge wind speed with the arrow vane and wind direction. Right now we're going to focus on wind speed. Wind speed is measured in terms of distance over time. How far has the wind gone in a certain amount of time? And there are a couple of different ways this can be done depending on what application you're using it for. You can do miles per hour, kilometers per hour. If you want to get a little more technical and finer tuned there, you can go meters per second. If you are dealing with any kind of sailing, you can use knots per hour. A knot is basically a nautical unit that it's equivalent to about 1.15 miles. So if you are measuring wind speed, you are going to want to know how strong that wind is, because the stronger it is, the more damage it can cause. Wouldn't it be useful if we had some kind of scale to describe the speed and strength of the wind? Well, conveniently enough, we do. It is called the Beaufort scale. The Beaufort scale, if I am not mistaken, originated for nautical use, as so many things related to the wind do. This was something originally that was used in navies to kind of describe the wind and what was going on. So the Beaufort scale, we use this to rank wind speed. It ranks wind not only based on its speed, but also on the impacts that wind has on the objects that it comes in contact with. So we have a scale on the left here, looking at our little chart here. That gives us kind of like hurricane categories, category 1, category 2. Well, we've got this with a Beaufort scale at a much kinder and gentler level. We can describe at each scale like how intense is that wind. And then we can see what the wind speed is at that scale. So if we look at, say, a wind force of 0 to 1, there's basically no wind. It's calm. This is if you start a fire in your chimney, that smoke coming out of the chimney is going to go straight up into the sky. It's not going to get blown in one direction or other because there's not any wind. Then we can go to something like, say, I don't know, a moderate breeze would be a 4 to 5. This is, you've got a nice light breeze coming in, your long lovely locks are floating on the breeze, your little eyelashes are fluttering. If you are trying to get your homework done out in the quad, your paper's probably getting blown all over the place. We move up to something like a gale. This is very strong, strong wind. This is like when you are walking against the wind, and it is really difficult to keep motivating forward because that wind is pushing back against you so hard. You feel like your eyelids are going to flip over top of your head. And then the highest one we have on the Beaufort scale, which is a rank of 12 or greater, is a hurricane force wind. This is a wind strong enough to cause widespread damage, and this occurs at wind speeds of greater than 73 miles an hour, or greater than 117 kilometers per hour. Wind direction, we use a compass. That is how we describe our winds. When we come up with names for winds, they are basically referred to based on the direction they're coming from. Winds are named for the direction from which they originate. Almost always. There's just one little exception. But their example here is a wind from the west. One that is blowing from the west towards the east is known as a westerly wind. Winds starting in the east and blowing towards the west, those are called easterlies. We got northerlies, southerlies, you get it. We could also describe those, calling them like northeast winds, southwest winds, or we can use the actual numbers on the scale. For instance, a 270-degree wind is one that is coming directly from the west. A 90-degree wind is one that is coming directly from the east. Let's see some more little options here. So there are 3 basic categories of wind names. Your winds, if they are named winds, they will fall into one of these categories. The first one is the names using the compass or the degree headings, like that 270-degree wind from the west. The next one can be a little weird here, but this is names given in relation to water and land in coastal areas or bodies of water, because guess what? This started with sailors, people who were out on the water all the time, and they would reference relative to where they were in reference to the land. So we have things like land breezes, sea breezes, onshore and offshore winds. We'll see those in just a second. These are names that have to do with the relationship between where your wind is coming based on whether it's over water or over land. And then we have the main ones we just used, like the names based on the prevailing direction of that wind. Your mid-latitude westerlies. That prevailing direction of wind is from the west. We call it the westerlies. Just a few examples of what I'm talking about. On your left, we have winds that are named based on the compass direction, whether that is by its actual direction, the word west, east, north, south, or by its degrees on the compass. 270-degree wind is one directly from the west. In the center, we have that land-sea kind of thing going on. Winds that blow from the sea towards the land are called onshore winds. This is the one exception where we're actually talking about where the wind is going to. But an onshore wind is blowing from the ocean or a large lake onto the shore. Offshore winds, the opposite. That is blowing from the land off the shore onto whatever body of water we're talking about. And then we have our prevailing winds. And the image you see here of this tree, this is something that's called being flagged or windswept. You see how the tree's limbs are just kind of like, almost like somebody grabbed them and pulled them in one direction. That is from year after year after year of being exposed to high winds that are coming from a prevailing direction. That's the main direction they come from all the time. And this actually influences the plant's growth. The plant's limbs move more towards shelter just to get away from the wind, and the actual force of the wind is kind of sculpting them as they grow. When we look at wind on a map, there are three ways to portray wind on a map. Something called wind barbs, wind vectors, and streamlines. And here we have examples of each. So if you look at the top, you see the little arrows. They look like arrows. There's a little feather at one end and then a shaft. These are wind barbs. These are very cool. They will tell you both the wind speed and direction. So it's just like an arrow. Think about shooting a bow. Where the little feather is, that's the back. That's where the wind is blowing from. And then the shaft is pointing towards where it's going. Then we can use these little barbs on the arrow shaft here to describe speed. If we have a big solid triangle like the one on the left, that is 50 knots an hour. Those two longer skinny little barbs there, the longer one represents 10 knots and the shorter one represents 5 knots. So if we look at our wind barb to the left, we have that solid triangle, 50 knots. If we look to the one to the lower right, it is pointing towards the northeast, so it is coming from the southwest. That's where our little barbs are. And so we have a southeast wind, and then we can count how bad that speed is, how much speed we have here, because we have 50 knots plus 10 knots plus 10 knots plus 5 knots, southeast wind at 75 knots. And then on the top there, we have a dead west wind. It is coming from the west, blowing to the east, and it is blowing at 15 knots an hour. Then we get down to wind vectors. These are disconnected arrows that you can kind of tell not only the direction of which way the wind is going, but also its speed based on how long that arrow is. And then streamlines at the very bottom here. These are continuous attached arrows. You can tell the direction. The streamlines themselves just show the direction of the wind. To tell the speed of the wind, you want to use the colors that are being used on the map beneath the streamlines. So next let's look at air pressure and wind. What does air pressure have to do with wind? Well, if you've been paying attention, you've probably guessed pretty much everything. We also have an instrument to measure air pressure. Our instrument, and do note this word because it might be on your exam, we measure air pressure with a barometer. There are a couple different kinds of barometers. We have a mercury barometer, which is the more old-fashioned of the two, and then an aneroid barometer. Typically, when we report our air pressure, we are going to report it in units of millibars, small mb, or hectopascals, which is going to be written like an HPA. And basically, they carry over. A millibar, 1 millibar is equivalent to 1 hectopascal, at least close enough anyway. This is just looking at some of the more notable air pressure readings over, the period of time that we've been taking meteorological measurements. Normal air pressure on the face of the planet generally tends to run from 800 millibars at the lowest to like 1100 at the highest. We have not ever actually, I don't think, recorded either one of those. We have gotten close though. Now, I have mentioned before that globally average air temperature, air pressure at sea level is 1013 millibars, 1013.23 or 25 to be exact actually. That's the average. But our highest pressure ever recorded was 1084 millibars in Siberia. And then the lowest recorded pressure that I think still holds the record was 870 millibars of pressure, and that was during typhoon tip in the Western Pacific in, I don't know, end of the 60s, early 70s, somewhere thereabouts. So why does the wind blow anyway? Well, as I mentioned before, if you've been paying attention in this class, you might guess that it has something to do about differential heating of the Earth's surface. And you would be absolutely right. The wind blowing is all about unequal heating. This relates to pressure because remember, warm air is less dense than cold air. It will rise. As it rises, not only is the pressure in it lessening because it is warmer, and as it rises, it expands, and as it expands, it cools. Well, by its expanding, you are also increasing the surface area of that parcel of air so that the same amount of pressure pushing down on it on a larger parcel, it's going to be less pressure per unit area. So warmer air, less pressure, colder air, more pressure because it's denser. We have those varying things between the thermal energy, the pressure, and the air density. With wind, we are worried about the air density, which affects its pressure, and then pressure affects air density, and it all gets started with the unequal heating of the Earth's surface. So we have two kinds of pressure when we're talking about wind and moving air parcels. We have thermal pressure. This is directly the movement of the wind. What gets it moving and decides where it's going to go is directly from heating. Those changes in the movement of wind, its change in its position, is in response to changes in temperature. Warm air is associated with low pressure, cold air is associated with high pressure. And remember that these two, cold and warm, are relative. Your weather person may tell you, wow, it is a low pressure system out there. And you go outside and you're thinking, yeah, it's not warm. I don't get it. Well, maybe it isn't warm. Maybe the temperatures are cold to you, but if that air is warmer compared to the air around it, it will still be a low pressure system. So let's remember, warm air is associated with low pressure. Cold air is it's associated with high pressure. The other kind of pressure we have is something called dynamic pressure, which we will get into probably in the next lecture. This is more of a forced kind of pressure. This is pressure that results from wind being displaced or forced into an area. There are three primary forces that will influence wind speed and direction. After differential heating that gets the ball rolling and keeps that air moving, the three forces that control wind speed and direction near the Earth's surface are the pressure gradient force, the Coriolis force, and the friction force. Pressure gradient force is what pushes that air and gets it moving and keeps it moving. Coriolis force, Coriolis effect, influences the direction of the movement of the wind. And then the friction force, this is something that is going to basically put the brakes on the wind. It's going to influence how fast that wind can go at a given level in the atmosphere. Is it up aloft, away from the surface of the Earth, or is it down close near the surface where there's a lot of things for it to bang into and slow it down? So starting with that first important force, the pressure gradient force, or you often see it abbreviated the PGF because it's a little bit easier to say and is a whole lot easier to write. The pressure gradient force is the force resulting from changes in barometric pressure, air pressure, across Earth's surface. So after that initial differential surface heating that sets things up, the pressure gradient force is the most important factor in setting the atmosphere in motion and then in determining its wind speed and the direction in which it is going to go. And I will bring your attention, please, to this second bullet point. Extremely important. Air flows from areas of high pressure to areas of low pressure. Oh, look, we highlighted it because it's super important. This governs so much of climate and weather. Air flows from areas of high pressure to areas of low pressure. Interesting point about this is that the greater the pressure difference between the regions, between that high and low pressure, the faster the air is going to flow between them, the stronger that airflow will be. Here's a little example from your textbook. Here we have a very cool looking old-fashioned kind of bicycle. We have the air outside the bicycle and we have air inside the bicycle tire. You will notice that outside the bicycle, the surrounding air is fairly low molecular density. Those air molecules are spread out. I mean, obviously they're a little bit denser down the further you get to the Earth's surface, but that makes sense. But in general, they're fairly spread out. When you take a tire bump and you push that into the tire and you forcibly push air into the tire to inflate it, those air molecules in that tire are there under a lot of air pressure. Notice how much more densely packed they are in the air temperature. Remember what I said. Pressure flows from locations of high pressure to locations of low pressure. If you go and you undo the valve stem on that tire, which way is the airflow from the tire going to go? It's not going to go from outside air into the tire. No, we had to shove that in there. But that air inside the tire under very high pressure, that is going to blow towards the lower pressure outside air. Here's another version of that. On your left, you have a location which has fairly uniform air pressure. If you look over to the western side of this box, the air density with height is pretty much exactly the same as it is on the eastern side of the box. But then if we look at the box on the right, on our western side, that air pressure is obviously much higher. There's a much greater density of air molecules on the western side of that box than there is on the eastern side. High pressure on your left-hand side, low pressure on your right-hand side. Let's look down at our arrows beneath it. Our top arrow says pressure gradient. Gradient means a slope. The difference between two different quantities, that's a gradient. Notice that it is pushing from high pressure to low pressure. That is your wind direction too. Wind always blows from areas of high pressure to low pressure. Oh look, we're just going to keep beating this poor little dead horse because we really want to hammer this home. Pressure moves from areas of high pressure to low pressure. Now we have a couple different ways that we can report air pressure. The first is, well, we have station pressure and we have sea level pressure. You have heard me use the term sea level pressure a whole bunch, and I'm sure you've heard it many times throughout your long and illustrious career as a humanoid on this planet. Station pressure is the air pressure that's actually measured at a air pressure reporting station. That's what they're reading on their barometer. It has not been adjusted to sea level. And then sea level pressure, that is the air pressure that has been adjusted to sea level. That is, basically we consider sea level ground zero. That is our zero starting point measurement for air pressure. So why do we care? What does it matter whether it's adjusted to sea level or not? Well, there are going to be differences between those pressure measurements taken at different locations depending on their elevation. We know from the last unit that as you go up in elevation, your air pressure is going to decrease. Those differences in elevation can make it super difficult to compare the weather and the wind and what's going on at two different locations. So what we do is we take all the air pressure measurements and we are using them to do meteorological forecasts or whatever, some kind of calculations, we adjust all air pressures to sea level pressure. There's kind of a formula for doing this. You don't need to worry about that. But doing this allows us to compare apples to apples and oranges to oranges, or in this case, everything to sea level pressure. And everything is even and fair, and it makes comparison between locations much, much, much easier to use sea level pressure. Here we've just got another image from the book, basically telling you exactly what I just said. How could we visualize that pressure gradient? We use something called isobars. Remember when we first got started in solar energy, I was talking about isotherms, and then in the last chapter we had a map with iso lines on it showing lines of equal relative humidity. I don't know what the name is for a line that shows equal relative humidity, but if you're showing a line or a map with lines that represent equal values for something, we use that prefix iso, means equal. So an isobar is a line drawn on a map that connects points of equal air pressure. We can use isobars to very, very quickly understand what we're looking at pressure-wise, whether it's high or low pressure, which direction the wind is going to be moving, and in a rough sense, we can't use like actual numbers, but give an idea like relative, how fast that wind is moving. How fast is the wind moving, say, in one location relative to another? Well, let's have a look. And here's another box representing another location. We're going to go from, say, we don't have numbers here, but your left-hand side of the box, we will call that location 1. And the right-hand side of the box, we will call that location 2. Notice that at certain stages throughout the box, we have different air pressures written here. 1020, 1016, 1012. And side note, when we are putting iso lines on, or isobars on a map, we go in increments of 4 degrees of pressure. So there's a difference of 4 millibars of pressure between each line on the iso map. So what we got here is we start with our high pressure. This is a lot of air density going on the left-hand side of that box. There is high pressure. It is at 1020 millibars of pressure. As you go to your right, notice that the pressure is decreasing. Based just on this, you would know that your pressure gradient is blowing from the left-hand side where the high pressure is to the right-hand side where the low pressure side is. So that tells us our wind direction. Wind moves in the direction from higher pressures to lower pressures. You can look at the measurements, the millibars on those lines there, and tell which direction the wind is moving. We could also tell, like roughly how fast the wind is moving. Is it moving really slowly or is it moving very quickly? And we do that by seeing how much distance we have in between those isobar lines. Because if you think about it, if we go from our very far left-hand side and we go to 1020 millibars, okay, if that took a long time, then it worked up gradually, that pressure increased or decreased, rather. What's going on here is that it's taking longer for that pressure to go down because the wind's not moving very fast. There's a long distance to cover there. As those isobars get closer together, that means it's taking less distance to change pressure, so it's happening much more quickly. So a couple things you need to know when looking at isobars: pressure gradients. The pressure gradient, the flow of air from high to low pressure, always runs perpendicular, or at least it should in a perfect world, to the isobars. When those isobars are very close together, the wind is going to blow faster because the pressure gradient, that big difference between the high and low pressure, is very steep. It is changing very quickly over a very short distance. So the wind's got to be blowing fast. When the isobars are farther apart, there is little or no wind because the pressure gradient is shallow. It isn't as steep. The wind is having a lot, if there's any wind at all, a lot longer distance for that pressure to change. Here's basically what I told you. If we start on the left-hand side at 1020 millibars, this is our high pressure. Notice that space between the far left side and the 1020 is fairly large. Our pressure gradient is going to be going from left to right because we are starting with our highest pressure on the left and our lowest pressure on the right. So that is the way the wind is moving. We look at the isobars. How widely spaced are they? Notice that we start out slow. There's a wide space between isobars. As those spaces become smaller, that wind is becoming faster. So our little diagram at the top showing you what I just said. We are starting with our high on the left-hand side, our low pressure on the right-hand side. The isobars over on the higher side are more widely spaced, so we know that that wind is not moving very quickly, but it is moving. As it flows towards the low, those isobars are starting to become more tightly spaced. The wind is speeding up, and by the time it gets to that low pressure, it's actually moving quite quickly. We don't have exact speeds because that's not what we need to show with isobars. We just need to get a sense of how quickly the wind is moving in different areas relative to other areas. If we look down at the map on the bottom, this is a pretty standard showing high and low pressure areas on the map. You will notice in this instance that our high is on the eastern side and it is blowing towards the low on the western side. Let's take a look here. If we look around our high, those isobars are pretty widely spaced, which means that those are really either there's no wind going on, but we know there is because we have a pressure gradient, or there's light winds. Stop, take a look at this, and kind of figure out in your own mind, where would the strongest winds be just based on the spacing of the isobars? Well, it's kind of marked here for you. But as we move towards that low pressure system and you see that the isobars are very tightly spaced, that means that the wind is moving quite quickly. There's a couple interesting things going on in this map. If you gave it a look, you might be going, okay, well, she just said that the wind always moves from areas of high pressure to areas of low pressure, but not all those winds are moving in the same area, same direction really. And where that one arrow on the right, starting at 1028, and the arrow coming out of it says light winds, that's not pointing directly at the low. What's going on? Well, two things actually. For one thing, the air around those high and low pressure systems is spiraling. For the next reason, that arrow and the air coming out of the high pressure system is not blowing directly to the low. It's because of something called Coriolis. Well, the Coriolis force. You've probably heard it called that, Coriolis force. Technically, it is not a force. I have a little problem with calling it that. Let me read the definition to you and you will see why. The Coriolis force is the perceived deflection of moving objects like the wind, ocean currents, airplanes, missiles, stuff you just threw at your little brother, things like that, in relation to Earth's surface. Notice the word perceived. This isn't actually a force, it's kind of an effect. So we're going to change this name here to the Coriolis effect. There, I feel much better now. Okay, what this is if you were to take an object or you yourself were to move, say you are in an airplane and you start heading straight from the poles to the equator. You have a target in mind. You're going to move straight. Well, in a world that did not spin with no rotation, you would go straight to your destination, no problem. However, our Earth spins, it rotates, and this throws a monkey wrench into everything. Two things you need to take away from this slide. Important to know about the Coriolis effect. In the northern hemisphere, moving objects appear to veer to the right, and in the southern hemisphere, they appear to veer to the left. Northern hemisphere right, southern hemisphere left. This Coriolis effect that we're going to go into a little more here in a second, you also need to know that it is strongest at the high latitudes, and the effect becomes less pronounced at mid-latitudes, and really there's no Coriolis force whatsoever to be noticed at like between 5 degrees north and south of the equator. At the equator, there's basically nothing. So what are we talking about here? All right, well, here's Superman. He's basically going to do just what I talked about. Superman is standing at the North Pole, and he's thinking, well, dang, I would like to go visit, I don't know, someplace in, I don't know, maybe I want to go to visit the Galapagos off the coast of South America, you know, go lay on the beach and hang with the iguanas or something. So he decides to start flying from the North Pole. If the Earth were not rotating at all, Superman would fly straight and he would land in the Galapagos, and the welcome committee of iguanas would be so happy to see him. However, that's not how this story plays out, because our Earth does rotate, and that causes his straight line to appear that he is actually bending. What's happening is when he takes off, he's going straight, but the Earth is rotating. So he might have been aiming for the Galapagos, but by the time he gets there, it's moved eastward, and he's going to wind up in Hawaii. He has, for all intents and purposes, curved to the right in his path. We are going to stop here in a moment or two and watch a real quick video on that so that you get more of an idea of what I'm talking about. And if you are watching the video that I am currently narrating on YouTube, you're watching it remotely, you need to stop this video at this point and either go search the video I have on the slide here on YouTube and watch it, or I have it linked in Moodle. You can just go onto Moodle and watch it. We've got a little bit more of the lecture going, so go watch this video, get a glass of water, get some air, come back, and let's finish the lecture. So there you have it, the Coriolis effect. It is the apparent veering of an object to the right in the northern hemisphere and left in the southern hemisphere when it is moving. Well, what does that have to do with isobars? Well, when we showed you the isobars, the pressure gradient going straight across the isobars, that's what we would get if the Earth weren't rotating. But because it is, that is going to cause our wind moving from high to low pressure to veer slightly to the right in the northern hemisphere. So it's going to kind of come in at those isobars at a bit of an angle. Now let's go back and remember that I said how much the Coriolis effect affects that veering depends on where you are at on the Earth. The effect is much stronger at the poles. It's negligible in the, it's not as intense rather in the mid-latitudes, and when you get to the equator, there's basically nothing going on. Your isobars would be running straight, perpendicular, 90-degree angle to the pressure gradient force. The other thing is that as the motion of whatever object we're talking about, in this case air, speeds up, that is also going to increase the deflection to the right. So slower wind is going to deflect slightly to the right, excuse me, as it moves from high to low, faster wind is going to deflect much more strongly. This is where we get our spiraling in those high and low pressure systems. We'll get into that a little more in just a little bit. Meanwhile, let's recap. If the Earth didn't spin, the wind would flow from the poles to the equator pretty straight, a meridional flow. That basically means from up and down, north to south, your latitude, excuse me, your lines of longitude, these are meridional. Remember the prime meridian? That's all that would happen because of the pressure gradient force. But because our Earth does spin, well, we've got some complexity added. And then we're going to take a look at our last major force that affects airflow is friction force. You are probably familiar with friction. As the air flows down a pressure gradient from high to low, if it is flowing aloft from high to low, it's going to have a nice, relatively straight shot from high to low. It's not going to be stopped by anything because there's nothing in its way but air. As you get down towards the Earth's surface, that wind starts to encounter bits of raised elevation on the Earth's surface, whether it's mountains, buildings, trees, people, whatever. It's going to encounter objects that are going to slow its movement because they are introducing friction. They are creating drag on that wind. It is going to slow it down. And what we're talking about here is something called the planetary boundary layer. Now remember when we did layers of the atmosphere, I said there were the 4 or 5 major layers? Well, you can subdivide those, especially when you get to the troposphere. We have the boundary layer, which is basically the layer of air that is in contact in some way with Earth's surface. Earth's surface is still exerting a bit of an effect on the airflow in that layer. The bottom of that is the surface layer. This is the boundary layer where that wind is really going to come smack dab in contact with Earth's surface. This is going to cause frictional drag, and that is going to basically put the brakes on your wind. Surfaces with less friction are obviously going to have less of an effect. If you are blowing over, I don't know, the middle of Great Salt Lake, there's nothing there. That's why they have car racetracks, the Bonneville Speedway out there, because there's basically no friction, nothing to slow you down. But as that wind continues blowing across the Salt Lake, and this is a real issue actually at Salt Lake because there is nothing to slow the wind down, and those winds get going really fast and they can carry a lot of sand and salt with them when they get to Salt Lake City. All of a sudden, our air has encountered friction. It just hit a city. There are buildings, there's all kinds of stuff going on. People have vegetation planted. It has slowed down the air. This is our friction force. So what happens when we combine all 3 of these forces or effects, the pressure gradient force, the Coriolis force, and friction? This is where we start to get the spiraling spin, the movement we see on high and low pressure systems like on a map. So that surface friction, when air encounters the Earth's surface, that counters the Coriolis force. It basically changes and bends the Coriolis force one way or the other more than it might otherwise be apparently bent. It produces winds. If we were talking about a high pressure system, the air for a high pressure system is starting out aloft. It is high pressure. It is moving down. It's going to go down to the surface of the Earth. Once it hits the surface of the Earth, the only way it can go is out. So we have diverging winds moving away from each other. As those winds move away across the surface, they are encountering friction, and this is bending them. So high pressure systems, our air will be spiraling clockwise in the northern hemisphere. With low pressure systems, the air coming out of that high pressure system is going to flow into a low pressure system because, pressure gradient force. In this instance, it's doing so towards the Earth's surface. It is happening down low. We have air coming in at all angles or all directions coming in towards the center of a surface low. When that air comes in, being slowed by friction, combined with the Coriolis force and the directions that they are heading in towards the center, is going to deflect them to the point where they will spiral in a counterclockwise direction. These are coming in, they are converging, just like we talked about at the ITCC. Those winds are coming in from all directions. They are smacking together in the middle and they are forced upwards. Now, they have just come up from the Earth's surface. The Earth's surface is warm. The Earth's surface is also where the majority of the moisture is. So guess what? They're going to be bringing warm, moist air up towards the upper atmosphere. That's going to cool. It's going to condense. We are going to get that cloudy, rainy, unsettled, unstable weather. Let's look at the next one. So then we're going to wrap up this lecture looking at that spiraling movement around those high and low pressure systems. And not only do we have a spiraling motion, but we also have vertical movement. What we call this movement around the highs and the lows is cyclones and anticyclones. A cyclone is the air that flows towards the low pressure region. As it flows due to the Coriolis force, it creates a counterclockwise circulation in the northern hemisphere. It's going to be different in the southern. It's going to be clockwise, but we're in the northern hemisphere, so cyclones spin counterclockwise. Around high pressure systems, we have what we call anticyclones. In this way, the air is flowing away from the high pressure region, creating a clockwise circulation in the northern hemisphere. We're going to get into these in a little more detail, go through them piece by piece, and I do have videos. They're not as descriptive as I would hope, but they're up on YouTube. There is one very good one. Or excuse me, they're on your Moodle page on those helpful videos. What we need to know here for right this minute is that most storms are cyclonic systems. Why? Well, if you think about it, because we're talking about a low pressure system. What did we talk about with low pressure? That air is rising from the surface up, and when it does that, it is more easily condensated. It causes clouds and unstable weather, and you are more likely to get cloud formation and storms. In some instances, we can get some really destructive storms going on. So let's diagram from your book showing you kind of the directions of movement of wind. Wind flows out from the center of a high pressure system. These are diverging winds at the Earth's surface. They are going down to the ground because it's high pressure, and they are flowing out from the center of the high. Low pressure is also happening at the Earth's surface because that is where the air from the high is coming into. So the air going into the center of the low is literally moving into the center of the low. It is directed towards the center. Those winds are converging, and then they will be forced upward. Meanwhile, while all of this is going on, we have our different directions of spiral. High pressure systems in the northern hemisphere spin to the right not in the right, but in a clockwise direction. Low pressure systems spin in a counterclockwise direction. The diagram at the bottom gives you kind of a 3D idea of what's going on. If that air is either converging or diverging at the surface, it is going to be doing the opposite thing aloft. We will talk about this more in the next class meeting, where I think I can go into it a little more detail and maybe use some examples to help explain it better. Meanwhile, let's stop and watch this video. And as before, if you are viewing this current video that I am narrating online, you can stop this video right now, go watch the video that I have listed on the screen here, which is once again up on Moodle, and then come back and we have one more slide and then we're done with the lecture. And then these are just pictures of two different cyclones going at different spots in the US, a little bit up towards Canada. On your left, we have just a basic everyday low pressure cyclone going on. This is, notice the counterclockwise flow. This is air flowing in towards the center of the low pressure system, towards the surface of the planet, down low. That air's got a lot of moisture in it. When it flows into that low center, it's going to converge. It's going to hit into each other. The winds coming in, they are going to be forced upward. This is going to cause condensation. And look at the clouds we got going there. The one on your right here, this is also a cyclone. This is a hurricane, actually, which is a form of cyclone. And the same thing is going on. We have counterclockwise spin. Air is coming in from all directions. In this instance, it's coming in over the ocean, so there's lots of latent heat there, lots of warmth, lots of moisture. So when that air comes in and converges in the center and starts to rise, it's got a lot of fuel to help it build a really big hurricane. And we will definitely learn more about this when we get to the section on severe weather.